Okay, I'm going to go over some of the R commands that go along with this chapter. I'm not going to recreate chapter or redo all the R commands you already see in there, so I'm going to kind of expand upon this and just talk about what they mean and so forth. Okay, now I don't have a CSV file to work with, so I'm going to bring in some data values. Okay, so that'll bring in to those data values to X. And then I'll do a print summary of X. Save that and run that. Yeah, did I save it? Oh, highlight it and run it. And we get this this printout right here. At least in RStudio, you have to make sure you highlight these when you run it. Minimum is smallest value, maximum is your largest value. First QU, that's your first quartile, Q1. Third QU is your third quartile, Q3. Your median is also your Q2, your second quartile. And your mean, remember, is the sample mean, population mean is the same formula. Now, some of these, you may be able to do the function directly. Like if I print mean, highlight that, and I don't know if I need to save it or not, but I'll do a run. And you see that just gives us our 7.875 directly. Now theirs is a little bit different. I have to go and look at this data set. Okay. So it looks like the ID, even though it doesn't make any sense to do a summary on that, it's doing a summary on that because it's in a separate column. The sex, since it's in a separate column, it's doing as much as it can. Obviously, it can't find the mean of those, so it looks like it's just doing a count. And then your height over here. Okay, so that's a summary, and you see how it works when you got 3 columns. So if you had 5 columns, you would have five of these going across. Okay, shows you a bar plot. Now here is the formula for the mean. I'm going to show how this is done, just so you see how you can calculate that. The mean by formula. This E looking thing here that's a sum from 1 to n, so that's all of our data points. So this is adding our x values together. And then we're dividing by n, our count. Now some of this I'm going to have to look up myself because I don't remember the exact syntax of it. I expect count is count, but let's see if that's a true statement. Highlight that and click run. Could not find the function count. Counts the number of fields, separates each of the lines of the file read. I'm not reading the line of files. Trying to think what other word would go with count. Obviously, I'm not going to think of a good one. R language count function. Data frame to be processed, variables to count, unique values of. I don't want unique values. Yeah, let's see. Counting elements in a data set. I don't count length. There it is. So print length of x. I've programmed long enough I should know that. 8. Okay, that's the one I needed. So back to our formula. We want to add together x values. So, and you can do this different ways. Now I know what that is. I don't need that. Sum or x sum is equal to the sum of the x values. And then if I print that, it's always good when you're doing these, do it a piece at a time. Don't try to write your entire bit. 63. Does that seem reasonable? I should have chosen smaller numbers. 6, 19, 21, 25, 33, 42, 43, 63, 63. Okay. Don't need that print there anymore. But I do need the count. So that's going to equal the length of x. And then I can find my, let's say it's x bar is going to equal to x sum divided by count. And then I'm going to print x bar. Run that. 7.875, which is the same as what I came up with up above, 7.875. So again, this does the uppercase sigma x. That's this up here. And then our n is our length. And so then you got your x bar is equal to x sum divided by count. Now, in case you're wondering, there's nothing wrong with using the mean function. So I'm just showing this as extra information on how to get used to R. Okay, this talks about the summary, some more there. You notice mu is the same formula. Sum of the x's divided by uppercase n. But that's the exact same formula. So whether you're finding x bar or mu, sample mean or population mean, the same formula. Now down here is this little o with a flip is lowercase sigma. So that's sigma squared. That's a variance. And it's interesting a way it refers to that. But population variance. S squared is our sample variance. And instead of this formula, you divide by n minus 1. Let's go through and find this using this formula here. Well, first off, I need my mean. That's mu. Well, that's good because we have our mean right here. It's x bar. So print the variance by formula. Well, I need to take x minus mu squared. So let's build that up. X, what in the world is x? X is x. Minus mu, which is our x bar. I could have probably said mu up above. But remember, mu and x bar are the same. Sample mean, population mean are the same. And then squared, and I think caret 2 is a possibility. Some programming languages allow it, some don't. So that's this right here. This is x minus x bar squared. Now we get a sigma in front, which means we want to add them together. So I'm going to have sum like that. Now that's adding them together, and that's all the top part. Then you want to divide by n. So I divide by, and you can type length directly in here, or since we already know the length, I could put count there. Now that's going to be our variance. So let me set that equal to something. This is sigma squared. So let's print sigma squared. And highlight that and run that. I have no clue whether that's right or not. Let's check it. We got 1, 5, 13, 2, 4, 8, 8, 9, 21. And var population of A1 colon A8 38.1094, and that looks right. Okay, now I'm guessing, and I don't have these memorized. I have to look them up, kind of same as you, to begin with. For somebody teach this class after a while, but there's probably a var formula if I had to guess. There is a var. What's this say? Compute the variance of x. Okay, so x. And let's see what that gives us. Now I'm wondering if that's not giving us the sample variance. So let's modify this. The sample variance, s squared. So s squared is sum x minus x bar squared divided by count minus 1. And now print SSQ. And let me highlight that. Aha, we see something here. Our var command gives the same as the sample variance. That's something important to keep in mind. If you got a problem that's asking you for population variance, using the var will not give that to you. var gives you the sample variance. And see, these are notes I'd make. I'd make a note. What does var give me? You know, what does mean give me, and so forth. Now, although I don't think they have it here, I guess they allude to it right here. The standard deviation is just the square root of that value we just found. So the standard deviation by formula now it's pretty much the same formula as you see up here, so I could copy this and do a print, and then or actually, what am I doing? Sigma is going to equal to, and now type square root and type in that value. I don't want the equals there. Now that's going to give us sigma s. We want to be the same formula, except for instead of count, I want to do count minus 1. Notice the use of my parentheses here. Order of operations. We want to, on the bottom, do the denominator completely, on top, do the top completely, the numerator, and then divide. That's why I put parentheses around count minus 1. Now if I do a print sigma and print s, now probably, I'm just guessing, there's a formula for standard deviation, SD. So let's see what that gives us. It's sample standard deviation, I believe. Okay, so sigma is our population standard deviation there. And then S, by formula, is this right here, gives us the same thing as the SD, which is our sample standard deviation. Why do they focus on sample instead of population? Sample is usually what you're working with. It's very rare when you have population values. Population values implies you have access to all the records. If you have access to all the records, it probably means you have access to the database. And there's not a whole lot statistics-wise you need to worry about, because you don't have to do any kind of inferences. You can just run reports and see what the mean is exactly, and no guessing. Okay. Now get us down here to a sample. Well, remember what our x is. There's our x values. What the sample gives you is they have this here first, which refers to the above spreadsheet. I believe. I'm not sure where they're referring to that at, but anyway, it's a data set anyway. And then comma 1. Well, if I do a print sample based upon x and I do 3, now if I run that, what this does is it takes a random sample from this data set here. So these x values, it chose 3 at random, and it came up with 4, 2, and 5. I am curious what it'll do is if you put in like 7. So let's try that. If I just highlight this and run it, you see it just runs that one line of code, and you say, well, how does it know what x is? X is still in memory. 8, 9, 13, 2, 21, 5, 1. 7, do 17. Okay, gives us an error. I was wondering if it'd give us duplicates. Let me try this again. I guess I ought to have it highlighted. Let's try that one more time. Okay, I'm not seeing duplicates anywhere there. So the sample looks like it doesn't give you duplicates, which is good. But that's what the sample does. It takes a random sample from within your data set. This talks about reading in the population and assigning it to X. That's an interesting calculation. Notice that the object is a sequence of length, spelled wrong, 100,000 stores all the heights of the population. Probability we seek is the relative frequency in this sequency of values between 160 and 180. First, we'll compute the probability and explain the method of computation. Well, let's take a look at this piece at a time, because I'm drawing a blank on what that is indicating to us. Now I'm going to clean this up some, because I got a lot of garbage here now. Okay, get down to here. And delete that. There we go. By the way, if you just do X like that, it gives you the same thing. I just tend to put print because from a programming standpoint, it makes me feel better, but you don't have to have it. Okay, so X minus 170. Okay. So X minus 5, 7, 7. So this would take each one of those values and subtract 7. And then I take the absolute value of it. Now what this has given us here is if you go from 1 to 7, this gives us the distance, the absolute distance. We're going to come back to that because I'm not sure where they're headed with that yet. And we're checking whether the distance is less than or equal to 10. Okay, I'm starting to see where they're headed here. So if we're looking at the values between 5 and 10. That would be 5, 8, 9. So it'll be 3 of them. Okay. I might find the average between 5 and 10. So my low would equal to 5, my high would equal to 10, and the middle would equal to low plus high divided by 2. So instead of hard coding 7, I'm going to say X minus the middle, which should be 7.5, our middle. Let's double check that. Never hurts when you're programming to actually put that in. 7.5. Okay, so then X minus my middle, and they got less than or equal to 10. I'm looking at the difference between my middle, which is 7.5, and like the 5 or the 10, which would be 2.5. Okay, so let's see what in the world that gives us. An error. Unexpected token middle. Oh, I don't have minus. Never mind. So false, true, false, 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 true, true. True, true, false. Okay, that makes sense. That's returning a true everywhere I got 5, 8, and 9. The values between 5 and 10. So then they have the mean of this. So I'm going to copy that. And let me run that. So I get 0.375. So How many numbers do I have? 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 8. And I said there's 3. 3 divided by 8 is 0.375. So this is the probability. If I was studying a problem, this would be a problem to calculate the probability of picking a value out at random between 5 and 10. Okay, now let's try to generalize this a little bit more instead of hard coding values, now that we're seeing what it's doing. Okay, so we got our 5 and 10, and those can be hard coded. You could get it from the user, but that's fine. This is no longer hard coded, it's done by formula. I don't need to print that because I know that's working. X minus middle is okay. 2.5 bothers me though. I've hard coded that. And that means if I change these numbers, I have to redo this right here. Now this is the difference between the middle and the low or high. So I'm going to say difference is going to equal to my middle minus my low. And now instead of 2.5 here, I'm going to put the difference in. Okay, it should give us the same value. That shouldn't change. 0.375. But now we can change this. If I'm studying the probability of choosing a number between 2 and 4. Now if I run this, 0.25. Between 2 and 4, there's only 2 values. 1, 2, 3, 4, 5, 6, 7, 8, and there's 2 values, 2 eighths, or 1/4, or 0.25. Okay, so that's what they're doing there, is calculating the probability of picking a value between two numbers. And looks like they're doing another one there. I've generalized this now though, where you can easily change that. Now here's an interesting item, the distribution of x. So let's take a look at that and see if I can remember how to do this. That's even a bigger question. For temp in x, print x, print temp. It doesn't like something. Unexpected token. One, 5, 13 goes through 21. Okay. This is your standard programming. What this does is loops through each one of these numbers. Well, I want to figure the probability here, but they're all different, so that'd all be the same. That wouldn't be very meaningful. Not to mention I'd need to create a count. Okay, well, never mind that. Though if you have programmed in other languages, this is how you do a for loop. So like if I was computing the sum could say sum is equal to sum plus temp. I don't remember if I need parentheses here or not. I don't think it's like Python. I teach different programming languages, and I started getting them mixed up. See if that still works, or if I just broke it. Oh, it helps to actually do something. Print sum. Yep, doesn't like that. Expected comma after expression. Okay, well, never mind that. Obviously, I don't remember how to do the standard for loop. That's not the way R is designed. R is meant to work with data sets, not to go through it individually. Here's your expectation. Mean is sum of your x's divided by n. Okay, now let's take a look at this formula. This is referring to a probability distribution where you got x times p of x. What that means is maybe this represents the number of male children, and p of x is going to be the probability. There's a 0.25% chance you'll have one male child. There's a 0.30% chance you have two male children out of four if you have four children. Maybe this is 10%. What am I up to? 40, 65, so this would be 35. So then, let me get rid of some of these. This says to multiply x times p of x. So x times p of x. If I run that, 1 times 0.25 is 0.25, 2 times 0.3 is 0.6, 3 times 0.10 is 0.30, 4 times 0.35 is 1.40. Now this is a sigma here, which means we add them together. And that would give us our 2.55. That's this expectation of this random variable, and that's how you calculate it. So you put your x values in one data set, your p of x values in another data set, you multiply them together and sum them. Sample variance. That's this formula here. Well, I need to store off this. This is my mean, so I'll say m. And I'm going to build this as I go along to show you how it goes. Take your x value minus your mean. Wait a minute. Obtain sum of the square from the average divided by the sample. That's not your sample variance for that. Oh, here it is. Here's the formula I'm looking for. They're showing how it builds up and how it modifies. So you got x minus your expected value of x. So let's do that first. X minus my expected value of x. M is our expected value of x. Let me actually put EX there. That would represent EX. If I run that, I get this. That is this middle part right here. Then I want to square it. Well, that's easy. Put parentheses around it and put squared on it. And that gives me this. Then I want to take that times p of x. Okay, still pretty straightforward. That's times px. Run that. Gives me that. And then this sigma in the front means I want to add them together, which is done with a sum. And you have to do your beginning parentheses and then your closing parentheses at the very end. Now I'm going to have this equal to something, so I have it equal to var x, and then I'll print that off. Okay, so let me highlight that, and that gives us our 1.4475. So that'd be our variance. This shows the buildup of it, but that's how you'd implement it in R, is the way I just showed it. See if I did this 0, 1, 2, 3. And what do I got? 0.5, 0.25, 0.15, and 0.10. Now if we run that, 1.0275, which is the answer they come up with here. Now our standard deviation, we just take square root of that. So SDX equals square root of the variance. And then print my SDX. And that gives us our 1.01 so forth, which is this. That's it for that chapter. Hopefully those workings in R kind of give you a better feel for how to implement formulas, how to read them, and so forth. Now this does not replace the textbook. The textbook is very good at taking a CSV file and showing how to implement that.